Let's continue our discussion. To start with, let's continue our discussion on these Reisner-Nordstrom black holes. Okay, so you remember that the metric was ds squared in Schwarzschild type coordinates minus dp squared f of r plus dr squared by f of r plus r squared d omega 2 squared. F of r was equal to, what was it? 1 minus 2m by r plus q squared by r squared. Okay. We had motivated the claim that the Penrose diagram of this black hole is given by the following structure. This is a bunch of diamonds. And then midway between the diamonds there are these singularities. And this is, the asymptotic region of any one universe. This is scri plus, this is scri minus, this is the outer horizon, this is the inner horizon, and so on. This goes on forever. Okay, so this is another universe with its scri minus, its scri plus, and so on. It just goes on. Okay, now this is really weird Penrose diagram, and you might wonder whether there is whether this diagram is physical. And I told you last class that there is a very simple way in which you can see that this diagram is physical. And that simple way is just to understand the motion of geodesics that start out somewhere here and then do whatever they do. Okay? So the question I'm going to ask is, what if I've got a geodesic that starts out, even maybe here, somewhere here. I've got a geodesic. Let's make it a massive geodesic, not necessarily a null ray. So yeah, let's make it a massive geodesic because the null rays just go straight here. Okay, by causality. Okay, but let's make it a massive geodesic. So it starts somewhere here. Perhaps it starts here, and then it does something like this. It goes like this. We want to know what happens to it. Okay, so of course, to understand formal questions of causality and so on, these crucial coordinates are useful. However, to actually do dynamics, crucial coordinates are usually useless because they're so complicated. Dynamics, if you want to cross horizons, you shouldn't use Schwarzschild coordinates either. In order to study dynamics, it's much easier, it's by far easiest to use ingoing and outgoing Eddington-Finkelstein coordinates. So let's use ingoing Eddington-Finkelstein coordinates. Now this whole region here is covered by ingoing Eddington-Finkelstein coordinates, because ingoing Eddington-Finkelstein coordinates are based on these geodesics and become singular only at this surface. So as long as we stay away from this surface or this surface, okay, in this whole region the ingoing Eddington-Finkelstein coordinates are good. So what we're going to do is to study the motion of particles in these ingoing Eddington-Finkelstein coordinates. Okay, so first let's write them down. So you remember if we define u was equal to t, somebody help me, plus or minus?
T minus
r star, and v is equal to t plus r star. Okay. Then what we'll do is to work with the coordinates r, v, and theta. So these are the coordinates we're going to use.
As well as phi.
Theta and phi. Two straight coordinates. Okay. Now, if we move to these coordinates, this is an exercise we've done before. I'm just going to write down the answer, and you tell me if you believe it. ds squared is equal to minus dv squared plus 2 dv dr dv squared f of r plus 2 dv dr plus r squared d omega squared. Do you see how this is equivalent to this? Okay, to see this, just put the definition in here. Okay, so what we will get is minus dt squared f of r. That's clearly here. Okay? And then we're going to get various dr dt terms and dr squared terms. Now first, that the dr dt terms cancel is obvious. Why is that? This is because dv squared has 2 dt dr divided by f of r. Because by definition, dr star is equal to dr divided by f of r. So, and since dv was dt plus dr star, you'll get 2 dt dr by f of r. But this f of r cancels that f of r, and so, and the minus kills this. Okay, so that gets rid of the cross term. And then what about the dr square terms? Well, for that you just take this dr by f of r, the whole thing squared. 1 over the f of r is killed. Okay, so you get minus dr squared by f of r. But from here you get plus 2 dr squared by f of r. So you get plus dr squared by f of r. So we've gone through this before. I just wanted to remind you. Okay, so this coordinate system is the same as this coordinate system. And you see that the big advantage here is that this is roughly as simple as this. Schwarzschild coordinates are great because they're so simple. This is about as simple as that. Unlike these unlike these Kruskal coordinates, which are hell on earth.
Yes.
You know, you cannot solve equations in Kruskal coordinates. These are, you know, mathematicians' coordinates. There exists something on the other. Okay, but if you want to solve things, this is where you go. Okay, so we're going to try to we're going to solve for geodesic motion in this batch. Now we're going to simplify our lives by looking at just radial geodesics. Okay, so we will look at d theta by dt is equal to d theta by d tau is equal to 0, d phi by d tau is equal to 0. And it's consistent. If it starts 0, it will stay 0 by spherical symmetry. Right? You're not moving on the sphere, you'll stay not moving on the sphere. That's obvious. Formally by conservation of angular momentum. Okay? So, so we can consistently look at motion that's just in the r and t plane. Now, how do we understand this motion? All of you now, you know how to do this, but let's quickly remind ourselves. What we are supposed to do is to look at the Lagrangian, which has some m, but we don't even keep track of that because it goes away for equations of motion. Just g alpha beta dx alpha by d tau dx beta by d tau. Take this Lagrangian, vary it to get the equations of motion, and then put the normalization condition on dx alpha by d tau. These equations completely determine massive geodesic motion. Okay, now now you see that this Lagrangian is independent of t. So the two alpha and beta will run over r and t, because effectively we're setting r and v. Thank you, r and v, because effectively we're setting the angles to 0. Okay, so there are two coordinates. This is like a non-relativistic particle moving in a 2-dimensional space. One of the dimensions is r, the other is v. Formally, right? Now you know that this g alpha beta, it's there in front of you, and is independent of v. Okay, so whenever you have a Lagrangian independent of one of your coordinates, the momentum conjugate to that coordinate is constant. So let's immediately compute the momentum conjugate to v. Okay, so the momentum conjugate to v is what? It's just the derivative of this Lagrangian with respect to v dot. So that will be g v alpha dx alpha by d tau up to some normalization which we don't care about. This is equal to some constant. Is this clear? Right? Because v dot gets rid of this index and then you get a v there. Clear? Okay, so this is constant. So now we can just put in what GV alpha is. So we get minus f of r, let's call that v dot, dv by d tau we'll call v dot, okay, plus 1 times r dot. This 2 here is a fake, right, because VR, RV. So GVR is 1. Okay, this is equal to a constant, and this constant will turn out to be negative. So we'll call it minus E. Okay, so that's great. So this is equation number 1. Equation number, so that's, we've got one equation for v dot and r dot. But if we want to complete the solving, we need a second equation, because there are two coordinates. But we know that there's a second equation, it's just that the velocity is 1. Velocity square is to minus 1. So what is that? That is the equation. Yeah, exactly. So minus f r v dot squared plus 2 v dot r dot right is equal to minus 1, because GRR is equal to 0. So the r dot square term is not there. Okay, so this is equation 2. Now we have two equations, two variables, v dot and r dot. And what we need to do is to solve for v dot and for r dot in terms of E tilde and f of r. So we just go ahead and do that. Okay, let me do it here. Okay, so I'm going to use, okay, let's use this equation to solve for r dot in terms of v dot. So this gives us r dot is equal to, right, f of r v dot square minus 1 divided by 2 v dot. And then we plug that equation into here. Okay. So we get minus f of r v dot plus f of r v dot squared minus 1 by 2 v dot is equal to minus E tilde. Okay. Now this is some quadratic equation for v dot, because you multiply the whole equation through by v dot. This is quadratic, and do they cancel? No, because of the 2. Yeah, this is quadratic, this is linear, so this is constant, this is linear. Okay, so you can solve. I'm just going to quote the solution. Okay. Find it. Okay. This guy claims that the solution is v dot is equal to E tilde minus plus square root of E tilde squared, yeah, minus f divided by f. Yeah. Okay. And when you then plug this into r dot, okay, when you plug this into r dot, you will get r dot is equal to minus plus square root of E tilde squared minus f. Just as a sanity check, let's see if this is true. Let's see that we get this from here. Are we good enough to do that? So we need f times v tilde square. It's quite a pain, right? Okay, let's. This can come from this.
V plus minus R.
We substitute v dot. Okay, good. When we substitute v dot, then e cancels. Very good, because there's the f. So we substitute f times v dot. So then we get e tilde minus plus square root is equal to so we get minus e tilde plus minus square root is equal to r dot. Yeah, so that works, right? Yeah. Okay, so you can. Thank you. Okay, excellent. So okay, good. So far this was just algebra. Now we want to get some physics out of it. Okay. So the first thing we're going to do, I'm clearing this back. I'll keep this diagram. The first thing we want to do is to look at this equation. Suppose we're trying to describe the motion of something falling in. Clearly we need to choose the negative sign because r should be decreasing as proper time increases. Okay, so let's choose the negative sign. So we have r dot is equal to minus square root of e tilde squared minus f. Now remember that in last class we plotted this f. Okay? And f looked like this. F as a function of r, started off at 1 at infinity, then went down. We're looking at the black holes without an aqueous singularity. So it went down, cut this, then came back up here, and then went up forever. So if we want to have a solution, we have to choose e tilde greater than, let's say that we have the particle coming in from infinity. So e tilde is greater than 1. So let's say it's somewhere here. So what do we have? This is, we can write this equation as r dot squared is equal, or plus f is equal to the e tilde squared if we want, just by squaring. So this is a motion of a particle of mass, whatever, 2 or something like that, moving in a potential f with energy e tilde squared. Okay? So clearly when f exceeds e tilde square, the particle can't go further.
So the particle eventually goes, it's like a Newtonian potential problem, where the turning point is the intersection.
Exactly. Okay, so maybe I should plot here e tilde square. This is e tilde square. Okay, so let's say that that's e tilde square. Then when this point crosses this line, the particle stops. The velocity is 0. Okay, so the particle moves, it goes zoop, zoop. Okay, great. So we understand what's going on. But now when we go back from our fictitious classical mechanics problem to the black hole, you see how dramatic this is?
Yeah, this is below the inner horizon. This is
exactly.
inside the inner horizon.
Exactly. This is the outer horizon. This is the inner horizon. A particle falls into the black hole through the outer horizon, through the inner horizon. Then it reaches some r, and then it turns back. You see, this is how gravity was not supposed to behave. It's supposed to be attractive. But it's doing it. Okay? It's repelling the particle. This f increasing is repelling the particle. Okay. So once a particle has gone here, now what does the solution look like? Now it switches to this branch of the solution. R dot is positive. Okay. Now actually one thing I should say. When we went through these horizons, f went through 0. Now we've got an f in the denominator. So you may worry that everything we're doing doesn't go beyond, let's say, the outer horizon. However, look closely. We had the minus sign. So e tilde minus e tilde squared minus f. Exactly. Let's expand it. So e tilde minus square root of e tilde squared minus f. Now, we're worried about divided by f. We are worried about f being 0, so we can expand it at small f. Okay, so that's e
And e
tilde.
squared is always greater than f. That's why we can expand in the first.
That's right. Exactly. E tilde square is greater than f. Okay, so e tilde divided by f into 1 minus square root of 1 minus f by e tilde squared, which, when we expand, is e tilde by f into half f by e tilde square. So which is equal to 1 by 2 e tilde, perfectly smooth as f goes to 0. Okay, so even though we went through the horizons, because we were working with you see, we could have predicted this because we're working with ingoing coordinates, and ingoing coordinates are perfectly fine as the particle goes through here and here. Okay, now it comes to some maximum, some minimum r, and turns around. Now the particle starts going like that. It has to keep going up in time. It goes back in r. And eventually what's going to happen? It's going to come to this point. Now what should we expect? Because we should expect it to keep going. I mean, why shouldn't it? Horizons are fixed. But in our coordinates break down here. Okay? How do we see that? We see that because when we switch to this branch, so now we don't have the minus, we have the plus. And now there's a genuine singularity in this equation.
Could you please repeat that?
You see, when we take the motion, the particle's gone in, then we start coming out. We switch from this branch of the solution, the minus branch of the solution, to the plus branch of the solution. In the plus branch of the solution, we have e tilde plus square root of e tilde plus f divided by f. What made this non-singular? What made this non-singular was that this term cancelled this term, giving you this proportional to f. However, here when f is 0, this term is 2 e tilde. It's constant. Constant divided by f blows up. Okay? So dv by d tau blows up at this point. So when does that happen? This happens when the particle tries to cross once again through the inner horizon to come back out. Okay? And or what you would call the inner horizon. I mean, across this surface. But this is a surface where f was equal to 0. Okay? So this coordinate system is breaking down there. That's as we expect, because the v coordinate system is ingoing coordinate.
Yeah, I mean, that is the limit of this coordinate system. That's the limiting surface.
Limiting surface, so we should have expected it. It's not that physics is breaking down, the coordinate system is breaking down. Now suppose we want to follow the motion of the particle further. What should we do?
Patch together two coordinates.
Well, yeah. What should we do in a practical way? Well, we use outgoing coordinates for this patch. Okay. So what in our analysis, now our analysis doesn't know which patch we're doing. Patch is a patch, I mean it's, what in our analysis will change? Only
so the DVDR coefficient.
Exactly. The only thing that will change is that DVDR, 2 DVDR will become minus 2 DUDR. Now that is exactly equivalent to taking V to minus V.
Yes.
Okay? And basically, how do I say this? Basically what happens is that the relative signs switch here.
Yeah.
Okay? So that if you use minus plus here, instead of getting minus plus here, you'll get plus minus there. When you go through it, you'll see that that's the only change.
But even in that coordinate system, the integration constant would remain the same.
So, yes, because
I mean, when we patch this together, and that's
yeah, you'll have to check what. Yeah, it's probably best to patch at points of f equals 0 maybe.
Yeah. Yeah.
So then you'll be able to identify them clearly. But you see, you should do that carefully. But the main point is this. Now when this relative sign has changed, what happens? Now what is the non-singular solution? The solution where r dot is positive. Because it's the positive guy here that is paired with the negative sign here. That's exactly as we expect. Because these outgoing coordinates are good here. And so, in that coordinate system, now you can continue to follow the motion of the particle. And we'll just zoom off to scribe class of this other universe. Okay? So, although I've not shown you all details, I'm claiming that more or less what we've done already makes it clear that you can reliably follow the motion of the particle, of this geodesic, doing this. It's quite an amazing thing. It starts off with scry minus of one universe and ends up with scry class of another. Okay, you can call it's a different universe in the sense that there is a separate scry plus and scry minus. You could have observers living here doing scattering experiments here. In this place, this is their interior of the black hole. They have another black hole to fall into. It's not this one.
But they're still causally connected, right?
They're still causally connected. It's true. In fact, a geodesic has gone from one to the other. So different universe. If you don't like the name. I agree. And the fact that the geodesic has gone from one to the other makes that clear. You can go from here to here, then get reflected and go up. Yeah, I mean, it's true. It's true. What I meant by different universe is this, that, suppose you were setting up, see, the following thing never happens, okay? Because this is an artifact of dealing with eternal black holes rather than black holes formed from collapse. But imagine that this was the case in a black hole that you could form from collapse. Then you could start in a space-time with no black hole. In this space-time, you have one scry minus, another scry plus. There's only one place to be far away from everything. Now you can take a charged shell, make it collapse. And once you've done this, had it been that collapsing solutions would produce all of this, you could then go through the black hole and come out into a whole new flat space region. Okay, that's the sense in which I meant different universe. It's this whole new region which is unconnected with the black hole. Where curvatures are basically, it's a new place to live in flat space, far away from the black hole. The black hole you've forgotten about.
The only problem I have is why is it new? Right?
It's new because this whole region of space-time did not exist without the black hole. You had the kind of space we're living in, flat. The three directions in which to move. When you're far away from everything, it's really just flat. Then suddenly you create this black hole, and then there's an infinite number of these flat space regions to live in. Do you understand? Okay? Of course, this can never happen. It's ridiculous. And it never does happen. This Penrose diagram is cut off in any collapse situation. Never happens that a collapse procedure produces this. So all this is like playing around with the...
So is it, in a realistic collapse situation,
Yes.
Is it possible that there are more than one copies of a single factor?
I don't think so. I don't think so. Just on physical, I haven't carefully investigated this, but just on physical grounds it's ridiculous. How can you have some finite energy process producing an infinite new space in which to live? I mean, it just sounds ridiculous. And I've never seen an example. Certainly in uncharged things this never happens.
An infinite new space, but that doesn't cost energy. It could still happen, right?
Okay, maybe it sounds ridiculous to me. It's like playing God. You're creating a new place for okay.
Why you say cuts off? What's the cutting off thing? Black hole collapses.
Let me give you a Penrose diagram. Let's work in the uncharged case. Let me tell you what the Penrose diagram looks like for a collapsing. It looks like this. Okay, you got R there's some shell coming in, and you see only this part of space-time. This part of the space-time, this is inside the shell. Okay? So this part of the space-time has to be identical to a part of the Penrose diagram of a pure Schwarzschild black hole. Okay? Because it's just pure Schwarzschild. But the fact that there is this shell, the dust cloud that you guys have looked at, if you look at that thing, you'll have a Penrose diagram that looks like this, where this is just r equals 0. So things go here and come back here. So the whole, this whole part of the Penrose diagram of the eternal Schwarzschild Penrose diagram, this is roughly speaking this part of it. Okay? This part just doesn't exist. The matter part, this matter here changes the space-time so that instead of analytically continuing to here, just ends space at r equals 0 and comes back. Actually, if you study carefully this dust collapse model that we studied in class, you'll see all of this in detail. Okay? So this thing is not created.
What do you mean by this thing is not created?
I mean, suppose we had a collapse situation. You started here. Before you threw your shell in, you had you're just one flat space. How many ways are there of going to infinity? There's one way for a space-like guy, 2 ways for for light-like guys. Scry minus and scry plus. Now, in this black hole space, there are 4 ways of going to infinity. You could go here, you could go here, you could go here, you could go here.
Not from one place though.
Not from one place.
These
But
two diamonds are causally disconnected.
it's true. But there exists this stuff, there's place for lots of things to happen here, which just didn't exist before it. Okay? So this dust collapse process creates if it were to produce a Penrose diagram like this, would have created a whole new universe, by which I mean would have created a whole new infinite space in which people could live. All kinds of things could happen. Just seems ridiculous, at least to me. And it never happens.
This may sound philosophical, but if 2 regions are causally disconnected, what does it even mean to say they exist together?
Well, you could do the following experiment if you were brave enough. You could jump in, somebody from here could jump in, and they could shake hands. Okay, so it's not completely meaningless.
So I have a question. Is it always forbidden that, let's say you have some universe which starts without no black holes, and then if some black hole is created by any process in the far future, could it look like it's part of some eternal black hole?
Part of course.
Yeah.
All black holes look like part of an eternal black hole.
No, so some double. Let's say
You
you
want
start
an
with ADS or some ADS, and then you create some ADS Schwarzschild black hole. Could it look like some ADS Schwarzschild black hole
With 2 boundaries?
Yeah, with two boundaries.
I don't think so. I don't think so.
Yeah.
It would mean that dynamics in one field theory has created a second field theory. You start with a Hilbert space which is that of one field theory. How are you going to create another Hilbert space? I don't think, it just sounds impossible to me. And there's no example of this. Okay? But never say never. But just sounds crazy to me.
So where's the cutoff happening?
Yeah, the cutoff is happening here. This whole part of the Penrose diagram doesn't exist. The important thing is these things don't exist. There is no second asymptotic region. The Penrose diagram is just this. Remember, the flat space Penrose diagram was this. This thing, for asymptotic analysis, resembles a flat space Penrose diagram. It has one scry plus, one scry minus, just like flat space. Everything that's different in this geometry is different in some small region of space, which is reasonable. Do you understand? Excellent. Let's keep going. Okay, I think this is all I wanted to say about these charged black hole geometries. This stuff is some toy thing, but it is an exact solution of Einstein's equations. Now one should be very careful, very wary of saying, I have a solution, but it looks like some unphysical. Because this is exactly what Einstein said about Schwarzschild geometry. Refused to believe in the existence of black holes because it seemed so weird. But you know, his equations were smarter than he was. In the sense that these black holes, not only do they exist, I mean now routinely measuring their collisions in LIGO. It's amazing. I think one should be very cautious about saying, I see these solutions of the equations, but I don't like them. Should be very cautious about that. Okay, so you know, just this is what the equations give you, and okay, fine. Let's move on. Okay, for the rest of this lecture, what I wanted to do was to study a much more realistic astrophysical black hole, which is the rotating black hole. It's much more realistic, but it's also much more complicated. Okay, but it's in a way more interesting. So let's start. Okay, so now what I'm imagining is this. I've sent some cloud of dust, let's say, with some rotation, and I've let it collapse. Now this cloud of dust has to carry angular momentum. It did carry angular momentum. Angular momentum is not lost. Actually, I never went through the formula for angular momentum for you in general relativity. I should have done. Maybe in the next lecture I'll do it more carefully. But it's a simple generalization of the ADM formula. You know, the ADM formula, I'll go through this next time. But if you go back to your notes and look, you'll find that the ADM formula can be thought of as a certain tensor dotted with a vector, and that vector is d by dt. If you take that same tensor and dot it with the vector d by d phi, that gives you the formula for angular momentum. Okay, so we have almost all the structure we need to understand what angular momentum is in general relativity. I'll tell you about that in detail next class. Right now, let's not break the flow. Okay, so there's a way of measuring angular momentum in general relativity. Okay, it's a very simple extension of what we've already studied for energy. Okay, goes with the intuition that there's a conserved quantity associated with every Killing vector. Okay, d by d phi is the new Killing vector. Okay, so but for now, that's it. So I've got this rotating cloud. It crumps in and collapses. Okay, so what is it forms a black hole. What kind of black hole can it form? It was only in the 1960s. It's amazing, right?
50 years.
Yeah, almost 50 years after general relativity that this question was answered. And it's the kind of question that, really speaking, anyone who seriously considered the problem could have answered. It took a lot of ingenuity and so on, but you know, many things take a lot of ingenuity. The thing that was not done was it wasn't taken seriously, because nobody took black holes seriously. The question wasn't taken seriously. Okay, so anyway, so this guy Roy Kerr found this solution, and it's pretty complicated. I'm not going to try to derive it for you. I'll just write it down. Okay, it would be work to go through the derivation, but I'll just write it down for you, and we'll study various of its properties. Okay. So there are many coordinate systems in which this metric can be displayed. I'm going to use what I call Boyer-Linquist coordinates. At some point, I'll tell you about what I call Kerr-Shield coordinates. Okay, but let's start with one. This is minus 1 minus 2 one way of writing it. I have to define all these terms. I'll do that. Which is also equal to where? Okay, so these are just equivalent rewritings. Okay, in this form, we've made explicit each term: dt squared, dt d phi squared, dr squared, d theta squared. Here, the dr squared and d theta squared are the same as here. But what we've done is, instead of writing dt d phi, we've written as dt squared plus d phi minus something. Okay. Both forms have their uses. Okay, where what? Rho squared is equal to r squared plus a squared cos squared theta. Delta is equal to r squared minus 2mr plus a squared. Sigma is equal to r squared plus a squared square minus a squared delta sine square theta, and omega is equal to, by definition, minus gt phi by g phi phi, which is equal to 2mar by sigma. Okay, so it's very complicated, but everything you want, everything is defined. For instance, if you wanted to check that this was true, it would be easy from here. G t phi is this quantity. G phi phi is this quantity. The sine square thetas cancel. The rho squares cancel. You get 2mar divided by sigma. Okay, and so on. Okay, fine. Everything, most of the things here are definitions. So, okay. Now what can you see? Well, del del phi is a killing vector and del del t is a killing vector. So they're all here.
Okay, yeah. Any linear combination is also.
Yeah. Okay, so let's look at this. Let's look at this. Let's look at this geometry. Okay, firstly, what is A, what is M? M and A are constants. Okay? So what we have is a 2-parameter set of solutions labeled by 2 numbers. Why is this reasonable? It's reasonable because there are 2 conserved charges. There's energy and angular momentum. Okay? So the first thing that is really interesting about black holes is this. At least in 4 dimensions. If you try to find solutions of Einstein's equations, pure Einstein's equations, no matter, okay, that are static, time stationary, not evolving in time, okay, that have a certain energy and a certain angular momentum. Okay? There's this thing called the no-hair theorem, which basically is the statement that these are the only solutions, only stationary solutions of Einstein's equations with mass m and angular momentum, whatever it's going to be. Okay? I want to emphasize this again. The first really interesting thing about this is that if I give you the energy and angular momentum, and I ask you, what can the system settle down into in the sense that not evolve further in time? There's a unique answer to that question. this is quite surprising. Okay, it's quite surprising if you think about it. For instance, either you should have no answers or many answers. I mean, for instance, suppose we had classical mechanics and some potential. Okay, let's suppose our potential was like this, and I give you some energy and say, what is the solution so the answer so the thing does not evolve in time? There's no solution. Always the particle is coasting. I mean, you want a solution when things are not evolving in time, you give me the energy, tough luck, there's no such solution. Okay? First, in general relativity, over a large value of parameters, we always have a solution, and these solutions are unique. You know what this reminds you of? This reminds you of hydrodynamics. If you take hydrodynamics on a sphere, I give you the energy and the angular momentum, things will always settle down into the unique solution of hydrodynamics because viscosity dissipates things. Dissipative systems have this kind of property. That conserved charges can't dissipate away, but everything else dissipates away. Okay? Fundamental theories of physics were not supposed to have this property. But they do, in this case.
So the no-hair theorem is a statement about static space-time?
Yes.
Is there any
Stationary space.
Stationary space-time?
Yeah. No, there's clearly no further solution. For instance, on top of this, I could put a gravitational wave far away from the black hole. If I'm not insisting on stationarity, there are plenty of solutions.
Yeah.
Oh, clearly. Okay, but it's the question of stationarity. Okay? Fine. Now, that's the first thing. The first thing is that these black hole solutions exist in a two-parameter set. That's the minimum number that could have existed because two conserved charges. And they exist in two-parameter set. It's not like there are zillions of stationary solutions. That's already interesting. Now, next thing that we want to say about the solution is what? What are the killing vectors of the solution? Well, that's a fancy way of asking what coordinates don't appear in this metric. You can include charge of the solution. Okay? These solutions are known. Okay? However, they're complicated and I'm not going to discuss them. Okay. So, which coordinates don't appear in this metric? T doesn't appear, phi doesn't appear. So what are we doing? We're looking at a black hole that's rotating in the xy plane. Okay? And this is another quite interesting thing. You see, suppose you wanted to give something orbital angular momentum. In gravity, what do you think of? You think of the Earth going around the sun. It has orbital angular momentum. The phi position of the Earth is changing all the time. So clearly the solution does not have a phi goes to phi plus constant symmetry. Because phi is where the Earth is. However, this black hole solution, even though it's rotating, it carries angular momentum in the phi plane. It maintains d by d phi as a killing symmetry. There's a phi goes to phi plus constant symmetry. That's sort of weird. It's more like
a black hole is spinning. I mean, not an orbital angular moment.
Yeah, it's like a top.
Yeah.
It's like a top that's standing, right on its axis and spinning. Okay, this kind of thing has angular momentum, even though it maintains phi goes to phi symmetry. It's not unprecedented, but it's not like an orbit of a planet.
Isn't that symmetry forced on the solution while causing the
Yeah, and that's how it was originally found. But by now there is a theorem that says there are no other stationary solutions. All stationary solutions have this additional killing vector. Okay, so in trying to, I quoted a theorem which said that all stationary solutions are of this form. What does it mean that the solution is stationary? It means that there is a time-like killing vector. But the interesting thing is that all stationary solutions, at least in 4 dimensions, all these things go wrong in higher dimensions. But in 4 dimensions, all stationary solutions automatically turn out to have two killing vectors. That was not forced. I mean, it was forced in how originally Kerr found the solution. But it's more general. It's a consequence.
So if you will have two killing
Will have two killing vectors. And this is the only solution. This is the only solution, as you can see, it has two.
So only the time-like symmetry is forced and the angular comes about?
Is a bonus, yes. Okay? It's part and parcel of this claim that this is basically the only thing that you can, that is stationary. Stationary.
But then one could claim that collapsing black holes would never attain this state.
Why would one claim that?
One could, because something that is collapsing is not itself stationary in time, and we have a solution that says
It is stationary in time. But what we're doing is looking at it at very late times. We're waiting for everything to have settled down and then asking, then is it stationary? You see, this does not describe the early collapse because it does not include the matter. But what we're asking is, once the matter has settled down to wherever it's gone, then presumably nothing is changing. You know, the radiation has gone away. Everything should be now time independent.
we don't know it will settle down. It might as well oscillate.
It might as well oscillate, okay? But we know that these solutions exist. Yeah, it's true. Do you remember our discussion on Choptic scaling? Suppose I send a pulse of matter in, okay? There are two kinds of behaviors possible. If the pulse is broad, the pulse can just go through. It doesn't settle down. But if the pulse is narrow, it does settle down. So if things settle down, this is the only thing that they can settle down into. And this is an attractive solution, by which I mean, I take the solution and I hit it.
It's stable.
Yeah.
It is
Stable under perturbations.
And I wait for a while. What solution does it come back to? It comes back to one such solution.
so one has to show that also, that it is stable.
Yeah, the one has to show that also. You know, this is an interesting problem. It's a problem computing what are called the quasi-normal modes of the black hole. We won't have the time to go through that in our course. It's an interesting problem. It's solved by Chandrasekhar. He's got this big book on rotating blacks. Very impressive book. You know, I once heard a story of Chandrasekhar coming to TIFR to give some lectures. So he starts his lectures by saying, I'm just going to give you results. I'm not going to give you derivations. But if challenged, I will produce them. No, man, needless to say, nobody's challenged. Okay. Okay. Let's move on. Okay, so that's the second thing, that there are these killing vectors. Now, I want to understand, I want to get a sense of what physics in such a background is in various ways. So let's start simple. The first thing I'm going to do is to ask, is kind of try to study aspects of particle motion. By the way, it's possible to completely solve for GD6 in this background. It's not obvious that that's true. But it's possible. It's been done by Chandrasekhar and various other people. Okay. And there's a beautiful mathematical structure to that problem. We will not explore that in detail. We don't have the time. And at the moment, we don't even have the motivation. But what we want to do is to get a rough sense of the physics of these solutions. And we'll look at little aspects of the motion of particle motion in this background. So the first thing is that, of course, as we've seen, there are two killing vectors, so there are two conserved quantities. Let us look at the conserved quantity of angular momentum. Okay? So suppose we've got a particle motion. What is the conserved charge corresponding to d by d phi? I'm going to write it down and you tell me if you believe it. G phi alpha dx alpha by d tau. You see, it's the same thing that we did at the beginning of the class. Another way of saying it, by the way, which is useful for remembering, is u phi. U with the lower index phi is the conserved quantity. This is always true. If you've got a killing symmetry conjugate to moving a certain coordinate zeta, u zeta is the particle conserved is conserved in this motion. Okay? So now let us look at the motion of particles which move with angular momentum 0. Okay? So suppose I've got a particle which from very far away I send straight at the center, radially inwards. That guy clearly has angular momentum 0.
So, just a question. Even in very far away,
Mhm.
does the angular momentum vanish at
Okay, I should have said that. Yes, it does. Let's look at that. Let's look at that here. Fine. So something I should have immediately said. Let's look at what all these quantities are complicated, but let's look at what they become at large R.
Yeah.
Okay. So rho goes to R.
Yes.
Okay. Delta goes to R square. Sigma goes to R to the 4. And omega goes to 0 because sigma goes to R to the 4. Okay, let's look at this form of the metric. Okay, rho squared delta by sigma goes to r squared by r to the 4, so that's 1. Omega goes to 0, so that's just d phi. Sigma by rho squared is r squared. Rho squared by sigma by delta is 1. Rho squared d theta squared is r squared. You see that it's just flat space. Okay, so this coordinate system is constructed to manifestly be flat space and polar coordinates at infinity. Okay, so the guy, yeah, so we are far away, we are sending something with u phi equals, at infinity we send u phi equals 0. That's the same as u phi upper equals 0 at infinity, because at infinity we've got the standard coordinate system. Okay, so it's not moving in the phi direction at infinity. But now it comes into the black hole. It comes nearer to the black hole. We want to know what happens. So this equation is already very illuminating.
This u phi is not so much the angular momentum of the black hole as it is the
No, it's the angular momentum of the particle.
of the particle of the field, because that Lagrangian
This is a background in which we're looking at particle motion. This is the angular momentum of the particle, and you can separate that from the angular momentum of the solution because d by d phi is a Killing vector. For particle motion, the angular momentum of the particle is conserved. Okay, great. So the first thing that we see is that this is equal to 0 for such a motion. But now what does that mean? You see, that means that g phi phi d phi, yes, let's call that phi dot, okay, plus g phi t dot is equal to 0. But note this omega here is defined to be gt phi by g phi phi. No, we are now looking at the special case constant is equal to 0. 0 angular moment. Okay, so we get phi dot is equal to omega times t using this definition.
Omega times t dot.
T dot, thank you. Notice that this omega is a function of r. Omega goes like 1 by r cube as r goes to infinity. Okay? But the point is that as you go to smaller and smaller values of r,
The angular momentum increases.
this phi dot increases. So you take a particle, you try to send it bang to the center of the black hole.
It rotates.
It starts going around. In fact, you can check that it starts going around in the same direction as the black hole angular momentum. Okay, this is a phenomenon that sometimes general relativists call frame drawing. Okay, it's that. By the way, every object that carries angular momentum and is stationary, outside that object, like the top we talked about, outside the object, the solution is the Kerr solution. It's a unique stationary solution. So this frame dragging is not just a property of Kerr solutions. It's a property of all stationary solutions of objects carrying angular momentum. So for the Earth, or for the Sun, okay, that's some frame dragging. Okay, and what does it mean? It means that you take this particle, you shoot it at the Sun. Before you reach it, it starts. You shot it radially inwards, but it starts moving in the phi direction. It's quite incredible. It's like, it's like space-time is eddy and it's being stirred, and you move with it. Right? And you see this so simply. Okay.
So I have a sort of dumb question.
Yes.
So does the Kerr solution, in a sense, help distinguish Mach's principle from general relativity?
Does the Kerr solution help distinguish Mach's principle from general relativity? So Mach's principle is, why don't the stars, why? Let's address this right at the end. I don't know. Okay. I mean, general relativity presumably gives you an answer to Mach's principle.
That's why I'm very confused.
Because it gives you, perhaps the answer is boundary conditions, right? But anyway, let's talk about it.
What does asymptotic infinity mean if a space-time is rotating, and that's...
If a space-time is rotating, but space-time here is not rotating.
Okay.
You see? You see, this goes to 0
Yeah.
at infinity. It's just the region around the black hole that's rotating. Okay, this is a complicated question. We'll try to. Okay. Now, great. So we've already understood something quite interesting. Now, let's try to understand more. Let's try to ask. Suppose I am an observer, and I want to move on the trajectory d. I want my u to be proportional to del by del t. That is, in plain language, I want dx alpha by del tau to be equal to something in the t direction and 0 everywhere. Yeah, I want to sit at, what does it mean? I want to sit at constant theta, constant phi, and constant r. Okay, I want to be an observer sitting at constant theta, constant t, and constant r. Okay, then the only coordinate that's evolving is time. Okay, and I want to ask. Of course, this is not geodesic. We've seen that sort of already here. Okay. It's not a geodesic for many reasons. Firstly, because geodesics want to fall into R, want to move in R. Secondly, geodesics want to move in phi. Okay, but I want to do this. I've invested in a good rocket, and I've got a lot of fuel, and I want to do this. Okay, I want to know when I can do it. So what stops me? The only thing that can stop me is if my world line stops being time-like. Right, if my world line stops being time-like, then I cannot live on that world line. Okay, so I can do this. I'm clearing this part. We should just keep that metric on the board. So I can do this provided GTT is less than 0. That's the condition. Because that's the condition that my world line is time-like. Is this clear? Okay, but that is true provided rho squared from this form of is greater than 2mr. Is that clear? But rho squared, we know what it is. So that is true if rho is r squared plus a squared cos squared theta is greater than 2mr.
There are certain regions of theta.
Let's figure those. Let's stay at constant theta and look in r. Imagine we're doing that. So we want to solve this equation for r. So we have r squared minus 2mr plus a squared cos squared theta is greater than 0. Well, so let's plot this. Let's plot this object here as a function of r. Sorry, we wanted this to be greater than 0. Right. So let's plot this as a function of r. Suppose r is very large. Clearly it's positive. Okay? As r increases, this function increases. Okay. On the other hand, if r is very small, once again you have something positive. Okay? So now we have two choices. This curve can either do this, or it can do this, where it goes to some constants. It's not going forever. It's going to something like this. Okay? Let's assume parameters are such that it does this. We'll be able to figure out when that's the case. Okay? If so, the region where sitting at constant, moving only in time, the region where that's disallowed is between the two roots. So firstly, if there's a disallowed region, we have to have two roots. And secondly, we should avoid staying between those two roots. Okay? So let's see. So what are the two roots of this equation? Okay? So it's, what is it? Minus, what is it? 2b. Minus, so plus 4m. Minus b, minus, thank you, plus 2m. Plus b squared minus 4ac. So 4m squared minus 4a squared cos squared theta by 2a, by 2, plus minus. Okay, let's take a factor of 2 out. So r plus minus, we'll call it, is equal to m plus minus m squared minus a squared cos squared theta. Okay, so cos squared theta is bounded from above by 1. So if m squared is greater than a squared, then these two roots always exist. Okay, let us assume, and we will see in a while, that m squared must be greater. Let us assume that m squared is greater than a squared. Then in every value of theta, these two roots exist. And we get, one of the things that we see is if we start going from infinity, we start going to smaller and smaller r, we insist on using our rocket ship to stay at constant r, constant theta, constant phi. We can do this provided r is greater than r, now people give it a name, SL, what is stationary something, r, let me see what stationary number, something like that, I'll tell you what they say. Stationary limit, SL, stationary limit must be RSL, which is equal to square this business, m plus square root of r plus. Yeah, so r plus, let's not call this, we'll be using another, we'll use r plus for something else. So we just leave this unnamed, and the positive guy is m squared minus a squared cos squared. So we see the following interesting thing. Okay, we see that as we go further and further in, there comes a point where no matter how powerful your engine, you cannot stay still. In fact, this is true also in the Schwarzschild black hole.
But that is precisely the horizon, right? That's
No, this is not the horizon. We come. This is the edge of what's called the ergosphere. This is true also in the Schwarzschild black hole. But what we're now going to see is that we can do better if we allow ourselves to rotate. You see, in the Schwarzschild black hole, we couldn't stay still when we reached the horizon because we had to fall in. Okay? So, no matter what we did, once we went past the horizon, we had to go to lower r. Here, that was sort of intuitively clear. You see, you're spending all your energy putting your rocket boosters pushing away in the r direction. To push in some theta direction would be a waste of energy. But here that symmetry is not there. You remember geodesics wanted to rotate. So perhaps what's going on here is not that you have to move forward in r, or you have to move inwards in r, but you can stay at fixed r if you allow yourselves to rotate. So now that's the next thing we're going to check. Okay? The edge of this r SL is what's called the ergosphere. Okay? It is the region of space-time beyond which you cannot stay still without rotating. There will be another region of space-time beyond which you cannot stay still no matter what you do. That will be the event horizon. Okay? But there is a place where you can do better, where you can do better if you rotate.
But even at this R SL,
Yes.
the GTT changes sign.
GTT changes sign, but that is not necessarily
Certainly
the
an
event horizon. T is just some coordinate.
But if m is less than a,
If m is less than a, as we will
boundary and
see, m less than a is a solution with a naked singularity. It is a solution as bad as we'll see. Hang on for a minute. Yeah. Okay. Excellent. Let's keep going. Okay. So now the next thing. Okay, I'm clearing this. The next thing we want to do is to say, well, okay, let's say I'm not wedded to the t coordinate. After all, Boyer and Lindquist invented this t coordinate. Okay, maybe there's something special about r, but t and phi I'll allow myself to mix. So suppose I do the following. Suppose I want d by dt or t dot is equal to some constant times phi dot. Right, the other way around. Phi dot is equal to some constant times t dot. dr by d theta by d.
So that's a complete constant, dependent on nothing else.
Be dependent on nothing else. I just want to move with this constant velocity. Last time I tried to move with 0. Okay? I tried to move with 0, and now I'm going to try to move with any velocity, some angular velocity, not going to allow myself to move in r, not going to allow myself to move in theta, but I do this. Okay? So now I'm going to ask, when is this possible? Okay? So exactly as is being suggested, what is the, we want to find the norm square of this vector. So so let's say that we get t dot squared and we take a minus, then we will get minus gtt plus omega gt phi minus omega gt phi minus 2 probably.
Yeah.
And then minus g phi phi omega square. Okay?
Yeah.
So for this to be allowed, we need minus gtt minus 2 omega gt phi minus omega squared g phi phi to be greater than 0. That's the generalization of the condition we had before. Okay? So let's take a minus gtt outside into 1 minus 2 omega. Now this by definition is little omega, I think, including the minus. So that's plus, no, so that's minus, so from the overall minus outside. And then minus omega squared. Okay, it's not so nice. Right? G phi phi, but what? The what don't match? GT phi and GTT.
G phi phi has to be taken out.
Ah, you're right. Okay, let's not be so clever. Let us g phi phi. Okay, let's write g phi phi in terms of omega. G phi phi is gt phi. Phi plus omega squared by omega gt phi. Okay, now we just have to plug this in, right? Okay, let me get them the form that they wanted. You know, the way form they put it in is this. They wanted to write g phi phi with a minor into, just check this, omega squared minus 2 omega plus gpt by g phi phi. I think this had to be greater than 0. Less than? You're probably right. You're probably right. Yeah, there's a minus, yeah. Less than 0. Less than 0. Okay. Now, regard this as an equation. Regard this as an equation for capital omega. Okay? So what we're asking is, given a place, given a location, what range of capital omegas can we rotate with so that we stay at rest? Okay? So this is of course some quadratic equation which you solve the roots for, solve for the roots. I'm clearing. You solve for the roots of this equation and you find that the two roots are omega plus minus is equal to omega plus minus square root of omega squared minus g tt by g phi phi, which after some algebra can be rewritten as omega plus minus delta to the power of rho squared divided by sigma sine theta. Okay, we won't try to go through the algebra, some simple manipulation. Okay, so let's see. What this gives us is some interval. You have to check the overall sign, but it gives us some interval between, if you look at this carefully, you find that this capital omega has to lie between these two roots. Okay, let's call this omega minus and omega plus. Given a value of r, the omegas at which you're allowed to stay stationary lie between a minimum and maximum value. Why is there a maximum value? Well, you see, let's say you're at some value of r. Let's say even flat space. You're at some value of r, and you go at too large an omega, you'll move faster than the speed of light. So your trajectory will not be time-like. So clearly there's a maximum value. What is interesting is that in the black hole spacetime there's also a minimum value. Okay?
If we don't move fast enough, then we'll
Then-
get sucked into the gap.
Exactly. But we, okay. Now, you see, let's look what happens at RSL. At RSL, that is the limit.
The two roots would converge.
No, almost, but wait. At RSL, that was the limit. You couldn't be at smaller r and stay at omega equals 0. So do you see that means that omega minus is 0 at r equals RSL. But if you examine this expression, you find that if you go to smaller values of r away from this, what happens is that this range shrinks. So, okay, r decreasing. Let me draw this way. R decreasing. As you decrease r, this range shrinks. So, here at RSL, this was RSL. You could stay with omega equals 0, just. If you go to lower and lower values of r, you have to go to higher and higher omega. And at some point, these two come and meet. This behavior you can see by just studying this expression. Okay, so the allowed value is the shaded region. This is the allowed value. Okay, where do these things meet? They meet where this is a double zero, exactly. They meet where this is a double zero. Okay, and where is there a double zero? Either at delta equals 0 or rho equals 0.
Rho is never 0.
Yes, or maybe a theta equals 0 is one point, but always delta equals 0 happens first.
No, rho is never 0.
Well, theta equals pi by 2, r equals 0, rho is 0.
Rho is r square. The minimum value of rho square is r square.
Well, but at r equals 0.
Guys, I was confusing with the spherical.
Yeah. In fact, you will see that. Anyway, right. But it's true. Rho is basically never 0, at least the way we're looking at it. So where this happens is at delta equals 0. Now, below delta equals 0, there is no angular velocity with which you can rotate to stay at a fixed position. That feels like the event horizon. Okay? We will check in a minute that it is. Okay? So delta equals 0, event horizon. Now let's go back to our expression for delta, and this time we'll use r plus minus. So r is equal to what is it, 2b minus 2b minus b 2m plus minus 4m squared minus 4a squared by 2, r plus minus is equal to m plus minus square root of m squared minus a squared. Let us compare this expression to RSL, which was m plus minus square root of m squared minus a squared cos squared theta. Notice that cos
Plus, RSL was
m plus, thank you. Notice that this quantity
is greater than r plus.
exactly. This quantity is always smaller than this, but since it comes with a minus sign, it means that RSL is always greater than r plus. So RSL is greater than equal to r plus. R plus will be the outer event horizon. Okay? And we can draw the following diagram. we can draw the following diagram. There is this region here, and there is this bigger region. How big the region is depends on theta. At theta equals 0, these two coincide. 0 or pi by 2 or whatever, pi. These two coincide. But at any other value of theta, there is a region of space where static observers cannot stand. You cannot stand with omega equals 0. But you are still outside the event horizon.
You can still escape.
You can still escape. How will you escape? Well, by rotating. Okay? This region, the pink region, the region that is where you cannot stand at constant t, at constant omega equals 0. You cannot just be moving in the time direction, no other coordinate, but you are still not inside the event horizon. It's called the ergosphere of the rotating black hole. Okay? If you were interested in another coordinate, okay, constant not t but constant some particular omega, you will have a different ergosphere for that omega. Okay? Got by this diagram. Okay? But the ergosphere for time is special for the following reason. d by dt is the killing vector whose charge, conjugate to which the charge is energy. So inside the ergosphere is an ergosphere precisely because gtt inside is positive rather than negative.
Yeah, and here all the metric coefficients are positive, right?
All the metric coefficients. I mean, if you solve.
Yeah, the metric becomes positive definitely.
No, it doesn't become positive. It never can. There's this diagonal component.
Oh.
I mean the off-diagonal component.
Yeah, off-diagonal. Yeah.
So always when you diagonalize it, it's -1, 1, 1, 1, 1. Okay? It's just that the time-like coordinate is not in the t direction. Not at all in the t direction. T is a space-like direction, but there's some combination of t and phi that's time-like. That's why you could rotate and sit there.
Yeah.
Okay? Fine. Now, but why is it important that this gtt is negative? Why it's important is this, that because of that, particles can move both forwards and backwards in time in the ergosphere region. In t, not in their proper time, but in the coordinate t. Okay? And therefore,
what do you mean we can move both forwards and backwards?
a geodesic is allowed to move.
I mean angular moment, I mean t and phi relative.
T dot can be either greater than 0 or less than 0.
Yeah.
Perfectly consistent with having local positive energy. Okay? But now, if t dot is negative, it means that the it means that the t dot was one of the two signs. It means that the conserved energy for that motion, viewed from infinity, is negative. You see, since both signs are possible, then the conserved energy is basically just gtt. Okay? And therefore, you can, from such a black hole, extract energy. Because you can throw in stuff into the black hole. Let's say you've got a particle, you've got some process where you go into this ergosphere region. You throw out a negative d by dt energy particle into the black hole, and then you go back out. You will have managed to extract energy because you've thrown negative energy as seen from the killing vector d by dt at infinity into the black hole. Okay? So this already tells you that there is something very interesting going on here. Unlike for a Schwarzschild black hole, you are able to extract energy. Physical processes can and routinely do extract energy from rotating black holes. However, this extraction of energy comes at a cost. You see, there is always some vector here. Let's say that we work with this minimum. By the way, these omega plus and omega minus at what they become at r plus, I rubbed out that formula, but that just becomes omega at r plus. You remember we had omega plus minus something. So omega, which was a function of r, when evaluated at r plus, is sometimes called the angular velocity of the black hole. Okay, and because d by dt minus omega plus d by d phi is always time-like here. You may be throwing in things of negative energy, but you can never throw in things of negative this quantity. But this part is energy, this part is angular momentum.
You lose some angular momentum.
Exactly. So if you think this through, what it means is that if you extract energy from the black hole, you must also extract angular momentum. And there is a bound. The bound is that the angular momentum you extract from the black hole is always greater than or equal to some constant times the energy that you extract from the black hole. So what you do basically by this extraction process is slow down the rotation. So what you do is somehow extract the energy of rotation. It's like you slow down the top. You got this top.
No, but you do gain in angular momentum. The observer who's throwing in.
Yes, will gain energy as well as angular momentum. Okay. So you extract energy as well as angular momentum out of the black hole. It's like this, right? It's like there's a top on the earth. You can slow it down, but you can't mine it. You understand? It's not like you can take stuff from the black hole out, if you think of the black hole. But the stuff of the black hole is going around. So okay, you can slow it down. Put the brakes on. But once it stops,
It becomes Schwarzschild.
it will be Schwarzschild and you can't take stuff out more than that. Now, it's a precise version of this statement which we'll study, possibly the next class, which is that the area of the event horizon can never decrease.
Yes, entropy goes.
Right. So it makes clear what you can and what you cannot do in these black hole processes. Okay? But this is one of the things that are important about the ergosphere. Actually, the existence of the ergosphere has an interesting consequence. This business about you can take out and so on. I mean, this sounds like very. What does it mean really? How do you take it out and so on? There is a simple calculation that allows you to say that. And that simple calculation is this. Suppose you take a minimally coupled scalar field. You can do it with a gravity wave, but it's a harder calculation. You take a minimally coupled scalar field, and you let that minimally coupled scalar field have a certain omega. So you send it from infinity like e to the power I omega t plus
The killing direction in phi.
alpha phi.
No I alpha phi?
Everything has an I. Okay? So this mode carries some angular momentum and carries some energy. And you allow the angular momentum to exceed this bound. That is, you choose alpha greater than alpha omega greater than omega plus e. Have I got it the right way around?
And alpha greater than omega over omega plus.
E is omega. Yeah, maybe over omega plus. Just a minute.
Yeah. So you're saying this quantity has to be positive, right? ddt minus omega plus?
Yeah. L by E, so alpha by omega should be greater than omega plus. That should be somehow the, how do I do this? I wrote this wrong, right? Because I want this to be like rotation.
No. That was right. Or dimensionally that was right. What you wrote earlier. I mean, it could be up to sign.
No, okay, right. Just a minute. D by dt. How does it? Just alpha, if I do this, I get alpha omega. Let's call this omega tilde.
Yeah.
And this is omega. If I did that, I would get omega on one side and omega tilde alpha on the other side. Okay, that's good. Yeah. So alpha by omega is greater than some constant. This is probably one way of putting it.
The black hole angular momentum.
Angular velocity.
Angular velocity.
Yes. It's greater than this. Then when you send the wave in, when you look at the scattering experiment, you send in a wave with some amplitude, you measure the amplitude with which the wave comes out. You find that the wave comes out with a larger amplitude than the amplitude you sent it in with.
Super radiance.
This is a phenomenon called superradiance. And never happens with plain Schwarzschild black holes. Actually, something similar happens with charged black holes if you send in charged particles. Okay? So this is a superradiance is a simple way of extracting energy out of black hole. You send in a mode that carries some angular momentum and some energy. You let it bang against the black hole. Some of it is reflected out. What's interesting is that the amount that's reflected out is more than what goes in. Okay, so you extract stuff out of the black hole. So you can constantly, by putting waves onto black holes, extract their energy out in a very simple way. It's not some complicated process that you have to worry about.
Even this process would slow the black hole down.
Would slow the black hole down. It does exactly what we talked about. You see, it slows the black hole down because you're taking out some alpha and some omega. But the alpha is greater than this, a certain minimum. Alpha by omega is greater than some number. So slowing the black hole down more than you're taking the energy out. That's somehow very important. Okay, we better stop very soon. Let me say one or two more quick things and then we stop. Okay, great. Now, the next thing I wanted to do was to understand. Okay, so we've discussed this ergosphere. We've discussed this position being the event horizon. Delta equals 0 is an event horizon. Let me leave this as an exercise. Exercise. Show that the surface is a null manifold. Which had to be the case if it was really the event horizon. This cements our identification of delta equals 0 with the event horizon. Okay, great. Okay, so now what else? I was going to tell you about Kerr-Shield coordinates, but forget about them. Has two solutions. That's the outer event horizon and the inner event horizon. Exactly like for the charged case. In fact, let me just end this because I don't want to go on forever. Next lecture we can do something else. Let me just end this by telling you about the causal structure of the Kerr black hole. Oh, maybe we should. Okay, this won't happen realistically in 5 minutes, so let's postpone this next class. Next class I'll begin with the causal structure of the Kerr black hole. We'll discuss it, and then we'll move on to discussing the laws of black hole thermodynamics. Angular moment. We'll start with angular momentum. Any other clearing up operations we need to do that we never did? We should remember. Did we WKB we never talked about. We can do that also next. Okay. Okay, great.